Okay, so I think it's a good time to start. So I hope, welcome everyone. I hope you all had a nice weekend. So today we continue with it's a second lecture of Hotat on generalized symmetries. So thanks a lot, Hotat, to joining us at this late time for you, I guess.
No,
So we're looking forward to your lecture. And if anyone wants to ask a question, please do not forget to do it over microphone. So otherwise, Hotat will not hear you.
good. Yeah, thanks, Sergej, for the introductions. So today we'll continue with the second lectures about the generalized symmetries in quantum field theory. So last time I spent quite a bit of time doing some heavy liftings. So hopefully today you see more of the applications and more of the use of various things that we built up last time. So just to quickly recap what was covered last time. So last time we started by talking about how to rephrase symmetries in terms of various topological operators. And this gives us the basis to discuss various generalizations of symmetries. And in particular, last time we focused mostly on the first generalizations, which is higher form symmetries, which replace topological operators by higher coordination topological operators. And in particular, we discussed the examples of higher form symmetries in the case of Maxwell theory, which is the U1 gauge theories. And in that case, we see that there are two kind of one form symmetries. One is electric, one is magnetic. And one thing that's important with this symmetries is that they can be spontaneously broken. So as a result, we can use them to characterize various phases. So in particular, in the case of Maxwell theories, the symmetries are indeed spontaneously broken. And this leads to this is characterized. This is related to the fact that this theory is a deconfined theory, and because this is a continuous one-form symmetry which is spontaneously broken, then there is a corresponding Goldstone boson, and this Goldstone boson is nothing but a photon. And we also discussed the robustness of higher form symmetries in contrast to the case of zero form symmetries. That this actually gives a very good use of higher form symmetries. That even though if they're emergent, they are robust, so we can still make a lot of interesting predictions using this emergent higher form symmetries. Good. So this is where we stopped last time. So we discussed already about how to that higher form symmetries cannot be broken by local operators. So then one natural question is that how can one break higher form symmetries? How to break a higher form symmetries? So to break a higher form symmetries, the idea is that the rough idea is that we basically want to make the charge line, the line that are charged under the symmetries, to be endable. What do I mean by that? What I mean is that imagine that you have some line that you thought were charged under some one form symmetries. Okay. So now if these lines can end on some other operators, so this is a lines that can be opened up, can end on some operators, then this will break the higher form symmetries that these lines were charged under. So this can be argued for very simple reasons. So consider that there are some higher form symmetry operators that links with the lines. Okay, so this operators because this line is charged under the higher form symmetries. So if we shrink this operators, we expect to get some non-trivial phase, right? So this is the definition that is charged under the one form symmetry line. But on the other hand, if this operator is topological, then we could have bring it past the endpoint and make it shrink somewhere. But this shrinking would not result in any phase, right? Because in the process, it's a smooth process. It doesn't cross any other operators. So we get a trivial phase. So this tells us that there's an obvious contradictions between the two. And the reason why there's this contradictions is because we made the wrong assumptions. That we thought that there are some one-form symmetry operators that are topological, but if the charge lines are endable, this operator is no longer topological anymore. So that's why our assumption is wrong. So in other words, it just means that it just means that once the charge line is endable, the one-form symmetry operator becomes non-topological. And since it's non-topological, it means that we lose the symmetries. So it implies an explicit one-form symmetry breaking. Okay. So this is sort of the high-level way of thinking, or abstract way of thinking about how to break a one-form symmetries. And let me discuss one concrete example. So the example I'd like to consider is a famous model, which is what's called a abelian-Higgs model. So what is this model? This model is basically a Maxwell theory, a U1 gauge theories, coupled to a scalar field. Okay. So this is a complex scalar field. And then we allow to turn on some potentials for it. So this is the model we would like to consider. So first things to notice is that in this theories, the U1 electric one-form symmetry of the Maxwell theory is explicitly broken. It's broken explicitly. Why? Because using the previous argument, we see that the Wilson lines is now an endable line, right? It can end on the phi operators, which are charged under this. So that means that the electric one-form symmetry has to be explicitly broken. And this is not a surprise because remember that electric one-form symmetry comes from the Gauss law. But now because we have the dynamical matters, that means that the Gauss law actually has a non-trivial source term. So the currents for the electric one-form symmetries are no longer conserved, right? Because there's a matter currents that would comes as a source for the Gauss law. And another way to see that is that remember that in the case of Maxwell theory, how we described the symmetry actions. The way we describe the symmetry action is that it is characterized by shifting the gauge fields A mu by some flat connections. But now in this actions, because I have explicit A dependence, so this terms explicit this coupling between the electric field between the gauge fields and the scalars explicitly breaks the shift symmetries. Okay, so this is another way to see that we lose the U1 electric one-form symmetry. Good, but we still have the U1 magnetic one-form symmetries. We still have the U1 magnetic symmetry. Okay, and this will be useful for characterizing phases of matters. So I discussed this example of abelian Higgs models, and unsurprisingly, there's a knob we can tune. We can tune the values of m squared. So if we tune the m squares, then we can go between two different phases. So one phase is the case when m squared is very, very large. When m squared is very, very large, then we can just ignore the scalar, right? They are supermassive, let's ignore them. So we just left behind a free Maxwell theories. So we are essentially in the Coulomb phase, okay? And a Coulomb phase is, of course, a deconfined phase. We have free photons. And in this phase, the exact U1 magnetic one-form symmetry is actually is spontaneously broken. Okay, so we can, because this is a magnetic symmetry, so I'll just refer to it as magnetic deconfinement. Okay, so this is what happens in one phase. But one thing I want to emphasize is that let's look at what happens at low energy. Okay, well, let's look at what happens to this theory at energy below the mass of the scalars. So in that case, the theory is described by effective field theories. And this effective field theory, of course, would have the standard Maxwell terms. But because there are matter fields, there's phi fields running in the loops, so we will get some high derivative terms, right? If we integrate out the matter fields, we'll get some high derivative terms. And so we will, for example, get the terms that are suppressed by the mass of the scalar field, and which with high derivative terms. This is roughly speaking f to the fourth terms, okay? And so on and so forth. So there's a derivative expansions we can do. But notice that in this effective field theories, everything we have been written down are all in terms of the field strength. So that means that this effective field theory actually has an emergent U1 electric quantum symmetries. Okay. So this is connected with what has been discussed in the past, that even though the UV theory has no electric quantum symmetries, but it can emerge in the IR. And if it emerges in the IR, it don't emerge just at a single point. It actually emerges in an entire phase. Okay. So this is this makes quantum symmetry very different from the case of zero quantum symmetries. Good. So this is what happens in this phase. Let's discuss what happens in the other phase. So in the other phase, if we make m squared to be very negative, then the scalar field condenses. So when a scalar field condenses, it has a non-trivial vacuum excitation values, right? And in that case, we can decompose the phi field into the vacuum excitation values, and then together with rotating degrees of freedoms. Here I ignore the fluctuation of the magnitude, just for simplicity. So then at low energy, the theory is described by, again, there's the Maxwell terms, which comes for free. And then there's the terms that it inherited from the kinetic terms, right? So if we substitute it back, we get a term like this. And it's easy to see that, but this is nothing but, sorry, because phi is transforms under gauge symmetries, so we can gauge fix phi to be 0. So in that case, this is just a mass terms for the scalar. So also for the gauge fields. So in IR, the theory just becomes completely gapped. So the scalar field has been eaten up by the gauge fields and then becomes a massive vector fields. Okay, so this is in what's called a Higgs phase, and this is a truly gap phase. Okay, and we can now ask what happens to the U1 magnetic symmetries in this series, because remember that the only symmetry that exists in the entire phase diagrams is just the U1 magnetic quantum symmetries. So this is the only symmetry we can use to characterize different phases. Okay, so in this phase, what happens is that there's no Goldstone bosons, there are no photons, so the U1 magnetic symmetry better be preserved. So it's better not be spontaneously broken. So the exact U1 magnetic quantum symmetry is symmetry preserved. And what does it mean? It means that there should be magnetic confinement. Remember that what's charged under the U1 one-form symmetries, U1 magnetic one-form symmetries is the 12 lines. It's the row line of the probe magnetic particles. So if the U1 magnetic quantum symmetry is preserved, that means that there should be some confining potentials between two magnetic monopoles. And there should be some confining strings stretched between these two monopoles. And in fact, this confining strings is there, and one can see that already at a classical level. So what is this confining string? This confining string is nothing but the Nelson-Olsen string. So this is basically a string, and then it's characterized by the property that at infinity, we let this phase phi winds. Okay, so it's characterized by the winding of the phase phi. So it has a winding phi. But notice that if phi winds, it actually creates a non-trivial kinetic energies, right? So we have to compensate that. So that means that when phi winds, we should also let A mu winds. We should also create a non-trivial holonomy of A to cancel this variations of phi. Okay. So in particular, that means that if we go around the strings, we'll actually pick up a non-trivial holonomy of the gauge fields. And this holonomy is exactly 2 pi. And because this holonomy is essentially the integral of f inside the disk that's filled in, so and remember that this is nothing but the magnetic one-form symmetry operators. So we can see that this strings is actually charged under the magnetic one-form symmetries. So this is another characteristics of a symmetry, right? That if the symmetry is not spontaneously broken, there must be states, must be some objects that's charged under the symmetries. So in the case of zero-form symmetry, that means that there are some particles that charge under the symmetries. But in the case of one-form symmetry, that means that there are some strings, some extended excitations charged under the symmetries. And in this case, it's really this Nelson-Olsen strings. Okay, and as you see that if now I have two magnetic, I cannot let the two strings end, and we can let it end. But if we let it end somewhere, we need to absorb the magnetic flux, right? Because at every cross sections, there's a nontrivial magnetic flux coming in this directions. So that means that the strings, if it ends, it has to end on monopoles or anti-monopoles. Okay. So what we have seen in this case is that everything is as we expected. There are this U1 magnetic one-form symmetry is preserved, and there are confining strings that are charged under the symmetries, and these confining strings are confining the magnetic monopoles. So these are all consistent with the statement that this U1 magnetic one-form symmetry is preserved in this fact law. Okay, so let me just recap what we have been discussing in this case. So in this case, we have seen that there's a UV models that we were interested in. And in these models, the relevant symmetries is the U1 magnetic one-form symmetries. And indeed, there's a nontrivial phase transitions that happens if we tune this M square. And there are two different phases. And we can characterize these two phases using whether the magnetic one-form symmetry is spontaneously broken or not. This would not be able to do if we didn't recognize this magnetic one-form symmetries, right? And as we see that if the symmetry is spontaneously broken, then there are nontrivial Goldstone bosons. So this is an interesting fact. It's an interesting phase. And in the phase where symmetry is not broken, this predicts that the symmetry predicts that there are some interesting extended string-like excitations in the spectrums. Okay, so this is what we have seen in these examples. Is there any questions about these examples?
I have a question about your criterion of breaking. So this endable strings you started with. So to say that electric is broken. So my question is, what is the precise definition? So should we look into the expectation value of the open string and
you mean what do I mean by endability? Is that what you're asking?
Yes. So how you would diagnose that like in some phase or in general, like the symmetry is explicitly broken? Because like naively you would say that what you did in the abelian Higgs model is just like add local terms, right? So
that's very different because
so you diagnose it more precisely.
That's right. So first of all, let me say there are two things I want to say. So the first thing I want to say is that when I say to determine whether the symmetry is explicitly broken or not, we just checked whether the lines whether there's a non-trivial non-local operators with this line operators ending on some local operators. If you have such operators, then there's no way that you can have one-form symmetries that acts on this extended line operators. Okay, so but for example, in the case of free Maxwell theories, we have the Wilson lines, but there's no way we can open up the Wilson lines because if we open it up, it's not gauge invariant, right? But in this case, we can have a Wilson line end on this phi field. It's a gauge invariant operator, so that's why this line is endable, and that's why the symmetry is explicitly broken. And another thing is about what's the difference between abelian Higgs models and the Maxwell theories. They're very different in the following sense that in abelian Higgs models, we actually introduce a new field, right? We introduce a new field phi. and then we couple it to the matters. And this is a non-trivial process. We extend the degrees of freedoms. We introduce new degrees of freedoms, which is this phi field, and then we couple it. So in that sense, it's a very it's not like simply deforming the theories. If
right.
Mm-hmm.
And it's
Yes.
connected to your instability condition, right? Because with this field, you can end the string. So
exactly,
okay,
that's right.
I understand. Thanks a lot. I think there is another question here.
I have one question. So in the case of the U1 magnetic one-form symmetry, if you introduce a monofold, is this makes the symmetry breaking, like explicit symmetry breaking for this, right?
Yeah, that's correct. Yeah. So if you have a dynamical magnetic monopoles, then you will break the also the U1 magnetic one from symmetries. That's right. So that happens, for example, in lattice models. If I have a lattice models, then usually you'll have a dynamical magnetic one from symmetries. Sorry, dynamical magnetic monopoles. Yeah, dynamical magnetic monopoles.
And then in the Higgs phase, you can use Meissner effect to argue that the tooth loop is has area law, right?
No, actually, in that case, it's once you have dynamical magnetic monopoles, what happens is that you have this confining string, right? And at some points, it will be so the strings will carry so much energy, it would prefer just to break, and then let the string ends on the dynamical monopoles, just to shrink the strings and then ends on dynamical monopoles.
But
So
when you calculate the expectation value of this, the loop, the tooth loop, because of the Meissner effect, when you make the distance of two monopoles, and the energy is linear with the distance, right? And then the expectation value will be the area law for the tooth loop.
Yeah, that's a good question. But the point is this: like, the thing about superconductors, the claim is that if the world has dynamical monopoles, if they have dynamical monopoles, then Meissner effect is not exact. That if you make your string, like magnetic string, to be very long, eventually it will want to just break, and then so the area law is actually not correct in the strictly thermodynamic limits. Yeah, but in our real world, of course, we know that if there were dynamical magnetic monopoles, they are extremely heavy. So in that case, you can say there's an approximate area law, but it's not a well-defined. In thermodynamic limit, it will again becomes a perimeter law. You will see that it has obey like area law, but eventually it will obey perimeter law at roughly the scales controlled by the mass of the dynamical magnetic monopole.
Are there any questions? Yeah, please.
Hello. So your magnetic monopole construction depends on a particular gauge choice, and if so, then how do we see that this is like coming out as due to U1 restoration or these static monopoles?
It doesn't depend on my gauge choice. It doesn't depend on my gauge choice. So one thing about this Nelson-Olsen strings is that it always carry non-trivial magnetic flux, and that is the gauge invariant notion.
Okay. Yeah.
Mm-hmm. Yeah.
Are there more questions? No, I think it's
good.
No questions.
Good. Yeah. Good. Yeah. Thanks for the questions. Good. So now let me move on to discuss TIFR anomalies. So I hope that example demonstrates that the use of one-form symmetries in characterizing different phases and phase transitions. And now I would like to discuss another applications of high-form symmetries. And this is tied with this concept of TIFR anomalies. And it's also in the titles of the programs. So you might have already heard some of this from Asso's lectures. I didn't watch all of his lectures, but my impression is that he mostly discussed anomalies in the context of fermions. But one thing I would like to show you or demonstrate to you is that anomalies can exist without fermions. Okay, can exist without fermions. They can exist in bosonic systems. And even higher form symmetries can be anomalous. And there are actually useful consequences for this anomalous higher form symmetries. So the claim in the case of Maxwell theory is that the electric and magnetic one form symmetry has a mixed TOEFL anomaly. So what do I mean by a TOEFL anomaly? So for me, a TOEFL anomaly means that it's an obstruction to promote a global symmetry to a gauge symmetry. It's an obstruction to promote a global symmetry to gauge symmetry. Okay. So let's demonstrate this in these examples of Maxwell theories. So remember that we have an electric one form symmetry with the following two-form currents. And if we want to gauge the symmetries, we want to couple it to a two-form gauge fields. Just like in the case of zero-form symmetry, we want to couple it to a one-form gauge fields. Okay, so I'll introduce a two-form gauge field denoted by BE. And then it will has its own gauge transformations, which shift this, which is the gauge parameter is a one-form gauge fields on its own. And we also have a magnetic symmetries. And this is its current. And then we also introduce its corresponding magnetic two-form. Okay. So now, if we want to couple the theory to this gauge fields, then what we will do at the linear order, at the first leading order, is that we want to introduce a term that is proportional. Actually, for me, let me first just copy and paste this. Okay, so this is the actions we start with. And now we first introduce terms that are linear in this gauge fields, and then also linear in the currents. Okay. So these are the two terms we want to introduce at least the leading order. So that means that we'll have a terms like this. Like this, BE wedge star F plus a term like this, EM wedge F. Okay. Okay. So now let's ask what happens if we perform a gauge transformations. So if we perform a gauge transformations, then this term will be shifted because this is not gauge invariant, right? So we'll shift this by this. And this terms will be shifted by a term like this. But notice that this shift is actually benign because this is a total derivative terms. And in particular, it has a proper normalizations in the sense that F can have carry non-trivial fluxes. So that means that integral of F are always 2 pi times integers. And this integral of d lambda can also carry non-trivial fluxes. So it's also 2 pi times integers. But this whole thing's after integrating over a closed manifold, it's always 2 pi I times the integers. But this is good because if we shift actions by 2 pi I times the integers, we're shifting the Boltzmann weight by just 2 pi e to the 2 pi I, which is just identity operators, right? So that's why this terms, even though it naively appears as not gauge invariant, it's actually gauge invariant. Okay, so this term is good. And now this gauge transformation is actually problematic. So we see that these gauge transformations involve gauge parameters and a dynamical field. And we need to fix it. And the way to fix it is very simple. Is that we just need to shift also the gauge fields A mu under the gauge parameters. But this is not surprising, right? Because remember that the electric one form symmetry, what it does is shifting the gauge fields by some flat connections. But now we're just promoting this global symmetries into a gauge symmetries. So I'm just promoting that shift parameters into a dynamic into a space-time dependent field. That's it. Okay. So that means that now my gauge field A is not gauge invariant, but that's again okay. I can just fix this. Sorry. So if now A is dynamical, then this terms will induce the terms that exactly cancels this. So which is good. But now this term itself will not be gauge invariant again because of a gauge transformation is coming from this terms. But in the end, we can fix all the problems by just introducing a term like this. Okay. Good. So the claim is that these terms together with these two terms is gauge invariant under this gauge symmetries and this gauge symmetries. But now there's a problem. The problem is that these terms, which were gauge invariant before, is actually not gauge invariant anymore because my f is not gauge invariant. So what happens is that under the gauge transformations, we'll shift these actions by a term that is given by the integral of bm wash d lambda e. Okay, and I want to claim that these terms cannot be fixed by adding any local counter terms. I'll encourage you to convince yourself this is the case. And for example, you might wonder that what happens if I add a terms that is like that is proportional to this. So this would induce the gauge transformations that cancels this, but this will again has the problems because these terms would not be gauge invariant under the shift of bm by dn. So no matter what, if you add some local counter terms, you just shift the problems around. So there's no way you can make these actions gauge invariant by adding local counter terms. Okay, and this is a statement that these two symmetries has a mixed toph anomaly. And the reason why I say it's mixed toph anomaly is because if you just take any one of the symmetries, you have no problem to gauge them, right? Because if I just take magnetic symmetries, I don't need to add this, I don't need to add this. This term is invariant under the magnetic electric magnetic gauge transformations. So I have no problem to promote the magnetic symmetries into a gauge symmetries. Similarly, if I don't have those terms, that means that I don't care about magnetic quantum symmetries. I just want to gauge my electric quantum symmetries. Again, there's no problems. All those terms are invariant under these two gauge transformations. But the problem appears if I try to gauge both symmetries. So that's why they are a mixed toph anomaly. Okay. So the reason why I want to bring up this example is that this gives you two takeaways. One takeaway is that it means that anomaly is something that can exist without fermions. And second is that higher form symmetry can have anomaly. Okay, and good. Is there any questions at this point, or if not, I'll discuss anomaly inflow.
Question.
Yes.
So you're saying that the takeaway is anomaly can exist with the fermion. Do you mean that's for the higher form symmetry anomaly you can exist with the fermion? So with the zero form anomaly, can it exist without fermion?
Yeah, you can. For zero form, you can also exist without fermions. Like for example, the simple example is like SUN level K WZW models. So it's a CFT in 1+1 dimension. It has anomaly as well.
Thank you.
Yeah, thanks. Good. Okay, so now let me discuss anomaly inflow. So when we have a toph anomalies, well, it means that the action is not gauge invariant under the background gauge transformations, and there's no way we can fix it by adding some local counter terms. However, a toph anomalies can actually be cancelled by a one dimension higher SPT phases. Okay, so this is the idea of anomaly inflow. So a toph anomalies can be cancelled by one dimension higher SPT phases. So what are SPT phases? So SPT phases stands for symmetry-protected topological phases. A way to think about them is that they are essentially distinct symmetric phases with a unique depth vacuum. Okay. So in a sense, they are the most boring phases. There's nothing interesting in the infrared if you just want to study the bulk of the systems. And in the context of quantum field theories, they're also sometimes called invariable phases or invariable theories. And the reason why they are called invariable is because they are, if you think about their partition functions, in the presence of background gauge fields, it is always has it's always a phase. It's always just it always has unit modules. Okay. And what it means is just means that this theory always has the inverse theories, which is given by its sort of orientation reversal, or its conjugations. And if I multiply these two partition functions, they just give you identity. So in that sense, the theory is invariable, that you can just stack this theories with another theories to make it into a completely trivial theories. Okay. And this partition functions is the key of describing this symmetry-protected topological phases. So what it does is that it characterizes the response of the phases under the background gauge fields, under the background gauge field for the symmetries. Okay, and in particular, this partition functions has to be gauge invariant on a closed manifold. Good. So now let's discuss go back to the example we discussed before. We have the 3D Maxwell theory. We now place this 3 plus 1D Maxwell theories on the boundary of 4 plus 1D U1 electric times U1 magnetic SPT. So this is a symmetry-protected topological phases protected by both the U1 electric symmetries and U1 magnetic symmetries in 4 plus 1 dimension. So remember that the partition functions, also the actions, is not invariant under the gauge transformations. The Maxwell action is not invariant under the gauge transformations of these two gauge symmetries, background gauge symmetries. But this problems can be fixed if we put this Maxwell theories to be on the boundary of 4 plus 1 dimensional SPT with partition functions which given by this form. Okay, so it's proportional to BE wedge with DBN. And we see that if we do a gauge transformations on this partition functions, what happens is that it will acquire a term proportional to d lambda E dBn. Okay, and on closed manifolds, it's not a problem. So on closed manifold, this is gauge invariant, as we discussed before. This is a gauge invariant terms. That this things always integrate to be 2 pi times integers. So this phase is always a trivial phase. But on open manifolds, because this is a total derivative, so it introduces a non-trivial boundary terms, and that boundary terms is exactly what we have to cancel this. Okay, so on open manifolds, this terms is not gauge invariant. So, but this non-gauge invariance induce exactly a boundary gauge variations, which cancels the Maxwell theories. So this is a mechanism of anomaly inflow. That Maxwell theories has some anomalies, but its anomalies is cancelled by also the similar anomalous transformations of the SPTs, and together this combined systems is gauge invariant. Okay, and this is also important for the study of SPT, because SPT, we know that it always has interesting physics happening on its surface, happening on its boundaries. And this is just because that if you look at the partition functions of this SPT, it's not gauge invariant. And the non-gauge invariance is always some boundary terms. So that's why I need something on the boundaries to fix the non-gauge invariance. Okay. Good. So the reason why I want to go through this anomaly inflow is that it not only connect with the physics of SPTs, it also gives a very straightforward explanations of why a topology is an RG invariant. So it's invariant under renormalization group flow. And this is actually the key of a topology, because this is RG invariant. So if you're interested in studying some microscopic systems, you can compute this topologies in the UV. And now, once you compute this and you find this a non-trivial topologies, then you can use it to constrain what can happen in infrared. And in our particular case, this is our SPTs that living in the bulk. And here I allow the general coefficient K sitting in the front. But one thing that's important is that this K actually has to be quantized for this theories to be gauge invariant under a large gauge transformations. Okay? And the fact that K is quantized is very important, because under RG flow, this K can only change continuously. But if K were started with 1, and it can only take integer values, then there's no way this K would just jump right away to some other values, right? So that means that this K is actually invariant under RG flow. So the fact that a topology is RG invariant is also tied with the fact that this is actually a discrete quantities. So there's no way that it can change. There's no way it can jump under RG flow. Okay. So that means that because this K is quantized, so that means that under RG flow, the bulk is fixed. So it doesn't go through any interesting flow. So in IR, that means that it similarly has to find something in IR to match the same orthophenomies. And so this is the idea of orthophenomy matching, that UV and IR should reproduce the same orthophenomy. And this is a consequence of this anomaly inflow. And in fact, one can prove that if you have such SPTs, the boundary theories has to be a Maxwell theory for the case of K equals to 1. Okay, so this is this is a very particular fact about this anomaly.
Hello.
Yes.
Question. Hello.
Yes.
Did you write that T-hoop anomaly is the renormalization group? Okay. Any chance to give us the explicit mathematical expression how the RG flow equation and the relevant references?
Oh, you mean how to prove that orthophenomy is RG flow? Is there references for this?
Any mathematical expression for the RG flow equation?
Oh, good. So one way to characterize the orthophenomies is using this SPT. So so as I argued just now that this SPT take discrete values, so there's no way it can change under RG flow. So this is a sort of the tools that we use to characterize the orthophenomy. Good. Now I discussed the orthophenomies. And one thing that's nice about orthophenomies is that a orthophenomy itself, if you find it's non-trivial, you will find that it is intrinsically incompatible with a trivially symmetric gap face with a unique vacuum. So this is a sort of mouthful. This basically just means the most boring things we can have. So it's gapped, it's symmetric, and it has a unique vacuums. In particular, I rule out the case where there's non-trivial topological orders in the IR. So because when I say it's trivial, it means that it just has no topological orders in IR. Okay, but this is nothing but just saying that this is an SPT phase. So it's kind of interesting what happens here. So what happens here is that if you have an SPT, its boundary cannot host another SPT. That's basically what's the content of a orthophenomy. And a boundary of a SPT cannot be another SPT. Okay. And this is super useful because we can now use it to deduce interesting physics, to deduce some constraints in IR of some strongly coupled systems. So in particular, I would like to discuss an examples of SU2 Yamil's theory.
Hotta,
So, yes, please.
can you come back to just to this argument? So because like the claim what you are doing is about Max. So are you making a claim about Maxwell theory itself, right? So we have a theory which has two global symmetries. Imagine I'm not gauging anything yet, so it does not have to be on the boundary of anything, right?
That's right. Yeah, that's right. A theory can exist without a bulk. Yeah, that's right. Even if it has a topological.
Exactly. So now could you repeat there? But now this last line about it applies to the Maxwell theory itself or to the
it applies to Maxwell theory itself. Yeah. In the case of Maxwell theory, it's boring because it's a free theory. Yeah. Maybe I can, if you allow me to go to the next examples, there will be a more non-trivial examples.
Right, but I just want to understand the argument here. So the claim is that the theory itself with these two global symmetries cannot have a trivially gapped state. And now,
correct. Yeah.
Because if you would try it, how you would argue that? So if you try to could you repeat the argument for that?
Yeah. Let me give you a boundary argument. Okay, so the bulk is just to convince you that a topological anomaly is RG invariant. But then there's a boundary argument. So what is the content of anomaly? The content of anomaly just means that your partition functions are not invariant under the gauge transformations, right? That there's a non-trivial transformations that depends on the background gauge rules and the background gauge parameters. But what is the SPT phase? An SPT phase means that the partition functions is a phase on its own. And moreover, this partition function is gauge invariant. Okay, so since this partition function is gauge invariant, there's no way it can reproduce any anomalies. So whenever you find that two symmetry has anomalies in the UV, then in IR it just cannot flow to an SPT phase, which just means that a trivially symmetric gap phase with a unique vacuum.
I see. Okay, thanks. That's clarifies
good. Yeah. Is there any more questions about this? Good.
Can you hear
so, oh yes.
So about the statement that our tooth anomaly is RG invariant, how is this consistent with the abelian Higgs model where we didn't have U1 electric symmetry?
There's no problem. Emergent symmetry can develop mixed anomalies with the other symmetries. That has no problems. Yeah, that's right. Yeah. Yeah. Good. So let me now discuss SU2 Yamil's theories. This is sort of the last things I want to discuss in the case of higher form symmetries. Then we can move on to non-invertible symmetries in the last 40 minutes. This I'll not get into details. I just want to give you a flavor. And then if you're interested in this, I suggest you to read these articles, read these papers, which discuss this in great details. So the problems about that one they're trying to do is that they're interested in studying the IR dynamics of SU2 Yamil's theories. And it's widely believed that SU2 Yamil's theories has very boring vacuums. It's truly confined gap vacuums, so nothing interesting happening. But Yamil's theories, interestingly, has a parameters one can tune, which is the theta parameters. And you can tune theta from 0 to 2 pi. And importantly, theta equals to 0 and theta equals to 2 pi is actually identical. So theta actually is a periodic numbers, which is 2 pi periodic. And the reason why it's 2 pi periodic is because what theta multiply is actually what's called instanton numbers. And this instanton number is always in integers. Okay. So that means that if you shift theta by 2 pi, you're just shifting the whole thing by 2 pi I times integers. So the partition function itself is gauge invariant. And Yamil's theories actually doesn't have that many symmetries of interest. One symmetry that is of interest is what's called a Z2 one-form symmetries. So this is a symmetries that's similar to electric one-form symmetries in the case of Maxwell theories. So this is also a symmetry that acts on the Wilson lines. But now it's just a Z2 symmetries, and this Z2 is essentially the center of the SU2. And this symmetry, what it does is that it just transforms the Wilson lines by some phase. and this Wilson lines are labeled by representations, and in this case, it will and this representations, because it's SO2 representations, so we can characterize by their spin, the spin of the representations. So if the spin is integer, then they are charge neutral under the Z2 one-form symmetries. But if the spin is half integer, then they will transform under the Z2 one-form symmetry. So that's basically the statements of the Z2 one-form symmetry. And this Z2 one-form symmetry actually is preserved in the vacuums if the theory becomes confining. And then there are in fact confining strings in the IR that are charged under the symmetries. Okay. So these are all the symmetries in the theories for generic theta. But then at theta equals to 0 and theta equals to pi, there's something that's non-trivial happens. So this is what's called the time reversal symmetries. So time reversal symmetries, what it does is that it changes theta to minus theta. So that means that you will have time reversal symmetries at theta equals to 0, unsurprisingly. But more interestingly, it has symmetries at theta equals to pi. Because theta equals to pi, under time reversal symmetry becomes theta equals to minus pi. But as we learned that theta is 2-pi periodic, so theta equals to pi, it's actually time reversal symmetric. Okay, so I'm doing this very fast, and then I'm just giving you a statement. But then we'll discuss consequences of the statement. So the statement is that at theta equals to pi, there's actually a mixed orthophanomy between the Z2 one-form symmetry and time reversal symmetry. Okay, so there's a mixed orthophanomy. I didn't prove it to you. It's proven in this paper, and I won't have time to get into that. But I want to discuss what is the consequence of this orthophanomies. What can we do if we learn about this orthophanomies? So what it does is that it actually constrains the possible IR physics. So we can ask what happens to the SU2 Yang-Mills theories at theta equals to pi. So there are two possible scenarios. So broadly speaking, there are two possible scenarios. One is that the theory becomes gap. The other possibility, the other is that the theory becomes gapless. Okay. So the orthophanomy is not strong enough to exclude gapless phase. So gapless is a possibility. Okay, so let's discuss more what happens to the gap phase. So in the gap phase, there are again two possibilities. One is that we consider symmetric phase. The other is that the system goes through spontaneous symmetry breaking. That means that either the time reversal symmetry is spontaneously broken, or the Z2 one-form symmetry is spontaneously broken. This is again not excluded by orthophanomies. So there's nothing you can exclude these possibilities. But what the orthophonal anomaly can do is that it can exclude this possibility. So it can exclude the possibility of a symmetric gap phase with a unique vacuum. Okay, so this is excluded by a orthophanomy. So this possibility is excluded out. So that means that at theta equals to pi, you don't expect to be in the same vacuum as theta equals to 0. Because at theta equals to 0, this is what we expect. But then at theta equals to pi, it has to be a vacuum of a different nature. Okay. And there's another possibility that could happen is that you can use again a symmetric gap phase, but then you have a non-trivial topological order in the IR. That is also possible. And in principle, orthophanomy doesn't exclude this case, but there's actually a stronger result one can prove that is very specific to this orthophanomy, is that even this possibility is ruled out. So generically, orthophanomy doesn't rule out this possibility, but in this very particular case, orthophanomy is actually strong enough. It is actually enhanced to rule out this possibility. And this is a stronger result proven in this paper by Cordova and Omori. If you're interested in this, I'll suggest you reading this paper. Okay, so this is what you can do with this orthophanomies, that you can rigorously exclude some possibilities in the IR. And now we can ask, so what is the most likely scenarios that happens in theta equals to pi? So there are some numerics. I'm just quoting some numerics results, but then this also supported by various sort of physical arguments. There's no proof, but there's some numerical results. And what the numerical results suggest is that if I tune theta from 0 to 2 pi, what happens there is that at theta equals to pi, the the theory actually goes through a first order phase transitions. So at theta equals to 0, the theory is in what's called a confining phase. But then at theta equals to pi, the theory is actually in what's called oblique confining phase. What it means is that in the confining phase, you have monopole that condenses. But then in the oblique confining phase is the dion that condenses. So and at theta equals to pi, both monopole and dion condenses, but in different vacuole. So you basically has just two vacuoles, and then they meet, and then they exchange across theta equals to pi. And this vacuole, two vacuoles are actually exchanged by tangential symmetries. So this is consistent with this possibility. The tangential symmetry is spontaneous Bolkans, and you have a gap systems. Okay. So this is what you can do with anomalies. That this is something that's very easy to compute in the IR, also in the UV. But then now once you compute it, you can use it to deduce interesting physics in IR. So this is a use of one-form symmetries and autophonomy in the study of confinements and so on.
Question. Could you say a word or two about how the topological order was excluded?
Oh, okay. So this is actually a non-trivial things. So what that paper did is that they come up with a criteria, which is actually a very simple criteria, and then they prove that because topological order. Okay, the key idea inside that paper is that if a symmetry is preserved in a topological order, then that symmetry operator can actually open out in a topological way. That's actually a non-trivial statement, and but once you have that statement, then you can use that to constrain the type of partition functions that can exist in topological orders, and you find that there are no way this kind of partition functions are compatible with the autophonomy.
Hello.
Is there any? Yes, please.
Yeah. So you mentioned about the numerics results. So at theta equal to pi, there is a severe sign problem. So how do the people?
That's an excellent question. So that's why the numerics is not that trustworthy. Yeah. So what there are various things that people did. The one thing I understand is that people extrapolate. So people did very small theta, and then they just extrapolate to theta equals to pi what they get. So it's not a super strong numerics.
They do a Taylor series expansion in terms of theta or the free
Yeah,
energy.
that's right. So they roughly study here, and then they just extrapolate. Yeah.
And another question I had is when you mentioned about confinement, then when you consider monopoles, these are this instanton dions, or these are different kind of monopoles that you are discussing?
You mean this monopoles?
Yes.
Yeah. So this monopole picture is actually sort of heuristic pictures. So this is sort of drawn from this pictures that we discussed in the abelian Higgs model, right? In the case of abelian Higgs models, it's the electric matter that condenses make the monopole confine. So by electromagnetic dualities, if electric matters want to confine, then you can do that by condensing magnetic monopoles. So
Yeah,
this is kind of
yeah, I was confused because here there's a way to construct monopole because you have a scalar field present. But in this kind of a picture, there's no scalar field. So how do
that's a good question. Yeah. So in this there are no there are no stable monopoles you can construct. So this is kind of a heuristic picture. Yeah. Okay. Yeah. That as far as I know, no one make it precise, but this picture actually works pretty well for various things we want to discuss.
Thanks.
Yeah. Excellent question. Yeah. Any more questions before I move on to discuss non-invertible symmetry? Good. So if there's no questions, now let's discuss non-invertible symmetry. So I only have 30 minutes. I prepared something more. So let me just start with something high level, but I'll try to do it quick, and then I would like to discuss examples. So the high level things about non-invertible symmetry is that they are basically generalizations of ordinary symmetries by just modifying the criteria of what kind of fusion rules this topological operators can obey. And in particular, we replace the conventional group multiplication fusion by a non-invertible fusion. And what that means is that if I fuse two objects, two operators, I get multiple operators on the right hand side. Okay. So this is the key that we get more than one operators on the right hand side, multiple objects. This is something that you should probably already see in Julian's lectures, that he discussed this use of categories in condensed matters. So hopefully this is something that you have already seen. So in particular, that means that if I now fuse two operators, there are various different outcomes, right? That if I fuse dA with dB, I can get dC, or I can get dC prime, right? So there are various possibilities. And in a very, very particular case is that I can now fuse an operator with this orientation reversal. This orientation reversal is essentially conjugations, okay? So usually for ordinary symmetries, invertible symmetry, we expect that we should just get 1. So this is just the statement that the operators that implements the symmetry is unitary. But in the case of non-invertible symmetries, because there are multiple objects that can appear on the right-hand side, so it can be not just 1, it can also be 1 plus some additional stuff. Okay, and so on and so forth. So this is what's called non-invertible fusions, in the sense that the operator that you thought were the inverse of these operators is no longer the inverse of this operator, in the sense that if you fuse 2, you don't just get identity, you get additional stuff. So that's what people mean by non-invertible. But there's a more sort of down-to-earth consequence of this non-invertibility, is that this operator that implements the symmetries is no longer unitary. Okay, so that's another way to think about non-invertible symmetries, that they are operators that commute with Hamiltonians. They're topological, they're conserved, but they are non-unitary. Okay, so this is another consequence of this non-invertible fusions. And a second consequence of this non-invertible fusion is that they actually give you very different kind of symmetry actions that you can imagine. So here I've drawn how a symmetries would act for the case of invertible case. But for the case of non-invertible case, it's a little bit non-trivial, because what happens is that when I go from this picture to this pictures, I'm pinching this and this, right? I'm pinching this. But this and this locally, they just look like D bar and D dagger and D, right? And but now, if they fuse to identities, then this is the only possible things I can have. But because they can fuse to additional stuff, so that means that I can get something like this. Sorry, the arrow is not well drawn. So I can get something like this, plus something like this. Here we have dB that's stretched between the bubbles and the line. Okay. And now if I make this bubble disappear, then this just becomes the local operators. But this now becomes a non-local operators attached by this topological lines of dB. Okay. So what we have seen here is that this is the nature of this non-invertible fusion, or consequence of this non-invertible fusions, or a characteristic of this non-invertible symmetry. That non-invertible symmetry generally mixes local operator with non-local operator. This is a sort of a characteristic of this non-invertible symmetries. Okay. So this is all the high-level things that I want to say at this moment. Then I'm going to get into examples. Is there anything questions about this point? Good. So if not, then let's decide examples. And as I promised, everything I'm going to say has a realizations in Maxwell theory. So we are just going back again to Maxwell theories. And what I'm going to discuss is to connect electromagnetic dualities with this idea of non-invertible symmetries. So what is electromagnetic dualities? So if you ask someone study the undergrad electromagnetic dynamics, they solve the Maxwell equations. So they, if they're smart enough, they will recognize that this Maxwell equation actually has symmetries. And this symmetries is a symmetry that exchange electric field and magnetic fields, right? We get the same set of Maxwell equations. And this it just means that I send F to its Hodge dual. So this is a if we uplift it to the differential form language. But this is only a symmetries. I want to claim that this is only a symmetries of the Maxwell theory of the Maxwell equations, the equation of motions. It's not a symmetry of the full theory. What do I mean by that? What I mean by that is that remember that when we study U1 gauge theory, I'm working with the normalizations that the gauge flux is always quantized. It's always 2 pi times integer quantized. So that means that I have no freedoms to rescale my gauge fields A. And that means that electric couplings is actually a physical coupling that can be measured, has a physical meaning. But this is not surprising, right? Because in a U1 gauge theories, a charge are quantized. So if the charge are quantized, you can just take the 2 charge of the minimal minimal quantized charge, and just measure their Coulomb potentials. And from that, you can measure the electric couplings, right? So the point is that when we talk about Maxwell theories, there's actually not just one Maxwell theories. There's a family of Maxwell theories, and they are parameterized by the coupling, electric couplings of this Maxwell theories, and they are not the same theory, okay? And this is important. Good, so now we can, with this fact in mind, now we can ask how can we understand electromagnetic dualities or understand the symmetry of the equation of motions at the level of path integral. So the way we understand that is that we can derive electromagnetic dualities by rewriting the Maxwell equation, the Maxwell actions into the following form. So we introduce a field B, which is a two-form field, not a two-form gauge field, just a two-form field, okay? And then we write a term like this. So notice that B is quadratic. So that means that I can integrate B with no problems. Then I just recover what I had before. So if I integrate B, I find that the equation of motions is given by 2 pi I over E squared. There's a minus sign, star F. Okay, and if I substitute this back, then I just recover the Maxwell actions. So this is just an exact rewriting. And now we can do different things because now the gauge field A actually appears linearly. So I can integral A, right? So I can integral A. So if I integral A, well, I learned is that dB has to be 0. And that means that B is given by d of A tilde, where A tilde is some again a U1 gauge field, and then B is just the flux of this U1 gauge field. Okay, and now I'll just call it F tilde for simplicity. So now if I substitute this back, then what do I get? I basically get the same actions as a Maxwell theories, but now with a different coupling. Okay. And remember that Maxwell theories are not equal. Different Maxwell theories with different couplings are not equal. So that means that under electromagnetic dualities, I'm actually mapping one Maxwell theory at coupling, let's say E, to another Maxwell theories at coupling E tilde given by 2 pi over E. Okay? So electromagnetic duality actually map between Maxwell theories, different versions of Maxwell theories. And under this duality, because we know that B is equals to star F, and B is also equals to F tilde. So then we also learned how the local operators are mapped. So local operators are mapped as this, okay? And using how local operators are mapped, we can also understand how the one-form symmetries are mapped. So one-form symmetry currents, actually the electric one becomes magnetic one becomes electric one. Sorry. And because the symmetries are exchanged, so that means that the charge operators should also exchange. So that means that my Wilson line actually under the duality becomes the 'T line. And similarly, my 'T line under the duality actually becomes a Wilson line. Okay, So this is what I mentioned in the first lecture, that a 12th line doesn't have a local expressions in terms of the field. It's a disorder operators, but it can be written as written in terms of the dual field, which is this A tilde field, and this is nothing but the Wilson lines of the dual field. Okay, and this is another way to see that the magnetic symmetries, even though it doesn't act on the field in the original or duality frames, in the new duality frames, they actually act on the field. It acts on the dual gauge fields and shift the dual gauge fields by the flat connections. And this is an example that illustrates that the way we think about symmetry shouldn't be restricted to how the symmetry transforms the field. We should think about the symmetries in terms of these topological operators. And once there's some topological operators, then we can claim there's symmetries, and we look for some charge operators under that. Okay, so this is hopefully it's something that's illuminating with this electromagnetic duality. Is there any questions about this? Good. So good. If there's no questions, now let's discuss what happens to this electromagnetic dualities at some special point. So as I mentioned before, that electromagnetic duality generally map you from one point, one couplings to a different couplings. But there's a magic couplings we can tune to, which is when E squared equals to 2 pi, then the electromagnetic duality is actually map you back, right? So that means that electromagnetic dualities at E squared equals to 2 pi, it's actually asymmetries. So at E squared equals to 2 pi, electromagnetic duality becomes a symmetry. So if it's a symmetry, then it should have a sort of a topological defect or topological operator associated with that. So how do we describe this topological defect? So the way we describe it is the following. So this is a zero form symmetries. So we think of it as an interface between the theory before dualities and the theory after dualities. Okay, and then we just want to describe it using some interface. So that means that on the interface we should introduce couplings. Let me finish the sentence. We should introduce couplings that couples the fields on the left and the fields on the right. Okay, please. What was the question?
Yes, so the question is that you're saying that ENM duality becomes symmetry, but after the duality, the symmetry transformation on the left and the right, it's not identical, right? It can map to each other, but it's not identical. So what do you mean by EM duality is a symmetry?
Oh, sorry, can you say what you said again?
So if E square equal to 2 pi, I agree that the form of the action before and after are the same, after you do the duality, but the symmetry on the left and the right, before and after you do the duality, acting differently on the field. So what do you mean by the duality is a symmetry? I see that the form of the action is the same, but the symmetry before and after duality acting differently on the gauge field.
Oh, you mean like I map electric symmetries to magnetic symmetries and vice versa?
Right. So
yeah,
what do you mean by duality is a symmetry?
Yeah, but this is not a problem, right? It just means that this symmetries doesn't commute with electric symmetry. If you conjugate electric symmetry by the symmetries, then it becomes a magnetic symmetries.
Okay.
Yes. Yeah. And but that's a important point, and that actually has consequence. That has consequence. Okay. Good. So I now want to describe the symmetries defects as some interface between left field and the right field. And let me just propose the couplings. So coupling is that I just write the transassignment terms, a mutual transassignment terms that couple the left and right. Okay. And as you imagine that this is a mutual transassignment terms, is topological. So this is describing a topological defect. But now if I introduce this transassignment terms, then we can ask what happens to the equation of motions. So we can now vary the whole systems with respect to A left. So if I vary the whole system with respect to A left, then I get a term like this coming from this. and I get a term like this coming from the transaminase terms. Okay, actually, let me write this as I. So I use I to denote what happens on the interface. But now this term, I can do a I think I can do an integration by part and then make it into a form like this. So now it is a boundary terms, which is just a terms on the integral on the interface. Okay. So what we have seen is that the equation of motion on the interface receives contributions from both the bulk and the interface terms, and they together tells us that on the domain wall, on the interface, star FL is the same as minus IFR, and minus IFR turns out to be the same as star FR du. So this is just using the electromagnetic dualities using this map. Okay. So what we have seen is that across this domain wall, if I bring an F operator across it, it just becomes electromagnetic counterpart. It's just as if it's going through electromagnetic transformations, duality transformations. Okay, and the claim is that this equation is also compatible with the equation of motion from A right. So this suggests that this interface that I wrote down indeed implements the electromagnetic symmetry at E squared equals to 2 pi. And in particular, under the symmetries, if I bring a Wilson line across this interface, it actually becomes a 12 line. And the way to see that is that let's imagine that we have Wilson lines that are on some contractible loops. Okay. So then we can replace this using the Stokes theorems into the integral of FL on the disk that fill in this loop. Then we can use these equations. And this will tell us that if we bring it across, then it becomes the integral of FR tilde d squared, which is nothing but integral of F tilde R A, FA tilde. So this is nothing but the 12 loop on the right-hand side. Okay, so everything I described is consistent with the electromagnetic duality map. That it exchange electric magnetic fields. It map map Wilson line into 12 lines and vice versa. And now we can check what happens. Well, what is this symmetry? So what is the fusion of the symmetries? So we can describe the fusion of the symmetries by considering the following two interfaces. So these two interfaces will separate the regions into separate the Maxwell theory into 3 regions. So they each have their own field, and then we also have the coupling that couples that. So we have a coupling that couples them like this, coupling that couples them like this.
Can I confirm the boxed equation is just at the interface?
That's right. This is just at the interface. That's right. This is at the interface. Okay, so now what am I describing? I'm describing the fusion between D and D, right? Both of them are just operator D. So if I bring this interface very, very close, then eventually this gauge field A and just becomes a gauge field living on the interface. So what do I have? So what I have is that I basically just have a term on the interface that is given by AM wedge with D A left plus A right. Okay, and this AM just becomes some auxiliary field living on this interface. And we can integral AM. If we integral AM, what we learn is that it's basically telling us that A left equals to minus A right. What does it mean? It means that we're applying charge conjugations to systems. So that means that if I fuse D with D, I basically get a charge conjugation symmetries. And so what does it mean? It means that at E squared equals to 2 pi, the EM duality becomes a Z4 symmetry. And so En directly is squared to charge conjugations. We can do another sanity check, is that what happens if I fuse D with D dagger? So what is D dagger? D dagger is just the orientation reversal of D. So that means that I just put a minus sign in front of this Maxwell coupling. This mutual transaminase coupling. So if I have a minus sign here, then that means that I will have a minus sign here, right? And that means that I just constrains A left to be the same as A right. So this is nothing but an identity interface. It's just a transparent interface, kind of a boring interface. So this is consistent with the fact that D is a unitary symmetry. It's a invertible symmetry. So it's actually just if you fuse D with D dagger, it just gives you identity. Okay. So this is what happens at E squared equals to 2 pi. Electromagnetic dualities becomes a Z4 symmetry. Is there any questions about this? Good. If not, now let's go on and ask the following questions.
Sorry, can I
Let's
ask?
move.
How
Yes,
can I
please.
see the Z4? Did you
How
explain
does it-
anything?
Yes, so the Z4 is just because, you see, if I fuse D with D, I get charge conjugations. I get a, right, if I fuse D with D, I get an interface which tells you that A left has to become minus A right. So which is charge conjugation symmetries. And charge conjugation symmetry is squared to 1, so D squared, D to the 4th equals to 1.
Okay, thanks.
Yeah, thanks. Okay, so now let's ask what happens at E squared equals to 2 pi over N. So in this case, it's clear that the electromagnetic duality doesn't map you from back to your original theories. So it maps you from one theories to another theories. But this is not the end of story. So it seems like there's no symmetry transformations that will lift the theory invariant. But this is not the end of story because we can still construct topological interfaces, a topological defect. It's similar to what we have done before. So at this particular coupling, what happens is that we just have various factor of n that appears in the actions. So I also make these things, I also multiply these coefficients by a factor of n. So this is my new topological defects in this new theory, okay? And the claim is that this is again a well-defined topological defects. All the equation of motions are consistent. But now the equation of motion is a little bit more subtle. The equation of motion tells you that, sorry, there's a star I missed. Tells you that F left is not exactly the same as F right tilde. They're off by a 1 over n factor. Okay, and this 1 over factor is actually very, very important. Because of this 1 over n factor, that means that the Wilson lines actually has a very strange mapping. A Wilson line, remember, can be a contractible Wilson lines, remember, can be written as integral of FL on a disk. It's now mapped to FR tilde over n. So naively, you might want to write these things using the Stock terms as AR tilde divided by n over S1, okay? And think of it as the Atoff lines to the power of 1 over n. So it's like a fractional Atoff line. But remember that I'm working in U1 gauge theories, and the charge are always integerally quantized. So this Atoff line that we describe here, it's actually not not a valid gauge invariant operators. So what happens is that this is still a correct expressions, but this we are not allowed to use Stock terms to just write it on the boundary terms. Okay, and then think of it as some Atoff lines. So this is really, this is really a line operator. It's really becomes a genuine disk operators. Okay, so what happens is that if I bring my Wilson lines across my interface, I get a disk operator. So this, and what is this disk operator? This operator turns out to be actually the magnetic one-form symmetry operators. If you recall that the magnetic one-form symmetry is generated by the field strength F. So this is actually very much similar to what I have discussed in the very beginning about the general nature of non-invertible symmetry. The non-invertible symmetries will map you from a local operators to a non-local operators, and similarly, it will map you from a loop operators to a disk operators. So this is similar to what we expect for non-invertible symmetries. So indeed, if we study the fusions of the symmetry operators, what happens is that when I fuse this operator D with D dagger, I actually don't get identity. I get something more complicated. What do I mean by that? So the way to see that is that if I fuse these two operators, I get a new topological interface here with an important factor of n. So now, as before, I can integral AM. But if I integral AM, what happens is that it tells you that A left is not exactly the same as A right. It tells you that A left is the same as A right up to Zn gauge fields. So this is what this factor of n is doing for us. Okay, and that means that this interface should be thought of as what's called a condensation defect. What is condensation defect? A condensation defect, roughly speaking, is a defect that are made of lower dimensional defects. So in this case, this is a three-dimensional defects made of the two-dimensional defects, which generates the magnetic one-form symmetries. And what this condensation defect does is that it's summing over various different ways of wrapping around this magnetic one-form symmetries on these three-dimensional objects. So the precise formula is that we are summing over all possible wrappings of topologically inequivalent wrappings of this magnetic one-form symmetries on this three-dimensional volumes. Okay, and as you see that in this fusions, I fuse D with D dagger, I don't get identity. I get something more complicated, and this is what's called. That's why this is non-invertible symmetries. And this formula is consistent with this formula. The reason why I said that is that whenever you have some electric, sorry, I said something wrong, it's electric. Whenever you have some electric one-form symmetry inserted somewhere, then if you move your gauge fields past that, then you will be shifting the gauge fields by the Poincare due of this electric symmetry operators. And then since I'm summing over all possible way of wrapping around these electric symmetries, then that just means that I'm shifting A left by all possible Zn gauge field configurations. So this is consistent with what we get from this equation of motions. So the option is that at E squared equals to 2 pi over n, we don't have invertible symmetries, but we have a non-invertible symmetries. And that non-invertible symmetries, in some sense, is very much like electric magnetic symmetry duality. It almost implements electromagnetic dualities, except of this factor of 1 over n sitting there. And also, it's massing how the Wilson lines are mapping to across the interface. They map Wilson lines, which is the loop operators, to disk operators. And this actually has a consequence. The consequence is that now, suppose we place our spatial manifolds to be some, let's say T3, so we have some non-trivial cycles in that. So now let's imagine that we wrap our Wilson lines on some non-trivial cycles on this T3. Now you can ask, what happens if I act my non-invertible symmetries on this state? Because when I act these non-invertible symmetries on a Wilson lines, it's mapping this Wilson lines to a disk operators that fill in the regions, filling the disk that encircle or that is enclosed by this loop. But because this is non-contractible loops, so there are no way you can fill in this non-contractible loops. So the only possibility is that this operators will annihilate the states. So this tells you that this is an operator which is non-unitary, and it also has 0 eigenvalues, so it's also non-invertible. Okay, and this is what happens at E squared equals to 2 pi over n. And I think I almost run over. I think I basically run over time. Do you think I can get another 5 minutes, or just to tell you guys about what exactly is the meaning of this non-invertible symmetry?
Yeah, I think It's no problem with 5 minutes. Could I ask a question first?
Yes, please. Yes, please.
So I'm just a bit confused. Is it really a symmetry because it maps two different? It's a duality originally, at least you said, right? Because on this first, like it maps you from E squared to pi over n.
That's right. That's right. Yeah.
So could you explain why you say it's a symmetry since it changes?
Yeah. Yeah. So I say it's a symmetry. It has so it's actually related to what I'm going to say next. So you see here, you actually see a tension, right? In the sense that we do construct a topological defects. So in that sense, on that basis, I call it symmetries because it has a topological defects defines the symmetries. But then on the other basis is that we have electromagnetic dualities. So, but electromagnetic dualities doesn't map you from the theory back to itself. So there's no way that this topological defect is implementing the electromagnetic duality. So what exactly is this topological defect implementing? This is related to what I'm going to say next. Yeah, if you give me another 5 minutes, then I'll
so then
answer that question.
If you could explain the next slide, in 5 minutes.
Yep.
Thank you.
Yes, yes. So let me now explain. So as Sergej pointed out that there's no way that the symmetry is related to electromagnetic duality. Sorry, it's just an electromagnetic duality because electromagnetic duality is doing something strange. But it's mapping you to a different couplings. So what happens is that this non-invertible symmetry is telling that your theory is invariant under the following two things. It's invariant under electromagnetic duality combined with a Zn one-form symmetry gauging, the gauging of a Zn one-form symmetry. So this is this fact that allows you to make it into symmetries. So if I go back to these pictures, if I start with this theory, if I start with this coupling, if I apply electromagnetic dualities, then I go to this point. But you can use gauging to bring you back from this point to this point. So combining both operations, then you actually get symmetries that or get operations that leave the system invariant. So that's what this symmetry is doing. So let me say a little bit more about the give you a little bit more details. So if I start with the theory at E squared equals to 2 pi over n, which is this actions, what I can do is that I can first gauge a Zn subgroup of the U1 electric one-form symmetry. Okay, so if I do that, what do? I basically couple the theory to Zn two-form gauge fields, a dynamical Zn two-form gauge fields. Notice that once I couple the theory to dynamical Zn two-form gauge fields, f minus b is no longer 2 pi periodic. It's no longer 2 pi quantized, but now becomes 2 pi over n quantized because a Zn gauge fields has a holonomy which is given by 2 pi over n. So this suggests that we should define f minus b as 1 over n dA tilde. dA, okay, dA. So, and this A is my new U1 gauge fields. And so that means that the actions is actually equivalent to 4 pi over n f wedge star f. And here f has a proper quantizations now. And now using combined with electromagnetic duality, I basically get the same actions. What I get n over 4 pi f tilde wedge f tilde. So I recover exactly the same action as before. So the upshot is that this is a symmetry in the sense that the theory is invariant under electromagnetic dualities together with this Zn one-form gauging. Okay. And one thing we can check is that remember that there's this factor of 1 over n, right? And this factor of 1 over n is related to this factor of 1 over n. So this factor of 1 over n exactly reproduces this. So we see that the actions of local operators is also consistent with this interpretations that the theory is invariant under this combined action.
Okay, thank you very much. Questions?
I'm still confused following up on Sergej's question. Is this is this not an interface between different theories? Even though
Oh, okay. Yeah, this is not an interface between different theories. So actually, let me say a little bit about what I want to say next, and then I'll just close the whole lectures. So, good. So the essence of all this is that, in fact, you can prove that if, or not prove, you can show that if a 3+1D theory is invariant under gauging a Zn one-form symmetry, then you can construct a topological interface, sorry, a topological defect, which generates a non-invertible symmetry. So what do I mean by that? What I mean is that you can now considering the following interface to start with. So on the one side is your theory T, and on the other side is the gauge theory. Okay, so naively, these two theories are different theories. So that means that this is an interface that separates two different theories. But because the theories is very under gauging, so the two theories is actually identical. So that means that you're actually now considering just a topological defect within a single theory. And what we do on this interface is that we want to impose Dirichlet boundary conditions for the dynamical gauge fields that implements the dynamical two-form gauge fields that implements the Z gauging. Okay. So the claim is that once you do this boundary conditions, then you actually obtain a topological interface, and which generally is a topological interface between two different theories. But because the theory is invariant under gauging, so that's why this becomes the topological symmetries inside a single theory. And one can actually show that generally just abstractly show that if I fuse two such defects, D with D dagger, so I'm basically means that I'm implementing gauging on this tiny slab that is enclosed by these two defects. And this gauging of on a thin slab is nothing but what I wrote down before. It's just summing over various way of wrapping around the symmetries that were gauged. And moreover, you can also understand the weird symmetry actions that I described before, that a loop becomes a disk by thinking about what happens if you bring a charged line across this interface. If you bring a charged line across the interface, then this charged line is actually not gauge invariant on the other side, because remember on this side, we're actually gauging the symmetries, right? So your charged line has to be attached by some kind of Wilson surface, which is given by integral of B. And this Wilson surface turns out can be thought of as the symmetries in this theory. So this is actually an interesting fact that if you gauge discrete one-form symmetries in 4 dimensions, 3+1 dimensions, you actually get the due 3+1D, due one-form symmetries in these theories. And that due symmetry is basically generated by the Wilson surface. Okay, so this is what we have seen here. That this also explains why if I bring a Wilson loop across this interface, it becomes a disk. Okay, I hope this answered the question.
So let me just confirm. So I think I understand this now. It's because of the special value of the coupling constant that duality, doing the duality transformation and then gauging the Zn one-form symmetry leaves the theory invariant, and hence it's a defect in the same theory.
That's right. That's right. Exactly. That's right. Yeah. Sorry that I took a longer time. I just want to basically complete my lectures with your questions. Yeah. Good.
Okay. Any more questions? I do not see any. So let's thank Bhattat for these nice lectures.
Thanks. Actually, let me just end with the slides that for people who ever wants to read more about it. Yeah, something I didn't just quickly say that something I didn't get a chance to discuss is that in Z and lattice gauge theories, there's actually this non-invertible symmetries, and you can actually use it to deduce an interesting fact about the infrared physics of Z and lattice gauge theories. So if you're interested in this, I'll suggest you read these papers. And also, let me just end with this slides that for whoever want to learn more about the subjects, there's some good reviews to study. And also, there's actually there's another there's a summer school this summer in Paris that on these topics. If someone is interested to learn more. Yeah, thanks.
Thank you very much. Yeah. Okay, so this concludes our morning lecture, and let's come back at 11:40 for the second one. Thank you, Hotat.
Thanks. Yeah, thanks again. Yeah. Have fun, guys.